Hello, welcome to my video on infinite limits and vertical asymptotes. So today we're going to learn about limits and we're going to deal with the notion of infinity. So let's start off with a quick definition. First, let f of x be a function defined on a neighborhood of a. So values close to a, doesn't necessarily have to include a. Then we write the limit as x approaches a of f of x is equal to infinity. Okay. Or we write the limit as x approaches a of f of x is equal to negative infinity. And what this means is that f of x can be arbitrarily large as x approaches a. Or if we use this definition, because it could go to positive infinity or negative infinity, we could say that f of x gets arbitrarily large in the negative direction as x approaches a. So as x gets close to a, we can make this y value as big or as small as possible. Okay, let's take a look at some examples just to have some intuition and illustrations. Okay, so in our first example over here, our function f of x is in green. We have dotted red lines over here which represent our vertical asymptotes. So recall, a vertical asymptote is a vertical line that the function, our green function here, never surpasses. It doesn't cross it. So the green function here gets very close to the vertical line but never touches it. Same at over here at an x value of 2, and similarly here at x equals 4. So I have 9 problems for you to do. Pause the video, try them on your own, see if your answers are similar to mine. So by now you should have had time to pause it and try it on your own. Let's take a look at the first one, A. We're asked to find the limit as x approaches 0 from the left side, there's a small little negative here, of f of x. The value you should be thinking of is the value, let's say negative 0.0001, something very close to 0, but slightly to the left of it. So if we go slightly to the left and we go hit our function, notice it's very close to our vertical asymptote. So this is going to continue upwards forever, essentially giving us a value of positive infinity. Okay. So the limit as x approaches 0 from the left side of f of x is positive infinity. So it looks like it stops here, but that's just based off the drawing. You know, if you're getting really close to 0 from the left, this is actually going to continue forever. So you should envision these guys going down forever, this going up forever, so on and so forth. Using the similar argument where you're looking for the limit as x approaches 0 from the positive side, so we go slightly to the right of 0. So this value here, you should be thinking of 0.00001, something very close to 0 and small. And again, if we go hit our function, this is going to continue upwards forever, giving us a positive value of infinity. So this leads us to part C, the limit as x approaches 0 of f of x. So we have to remember, for a limit to be defined, the left-sided limit and the right-sided limit have to be equal. That's something we've seen in the previous video, very important. Since the left-sided limit was infinity and the right-sided limit was also infinity, then we could conclude that the limit as x approaches 0 is infinity. So it does exist, it's equal to infinity. Okay. Let's move on to the next example. We're taking the limit as x approaches 2 from the left side, so slightly smaller than 2, so a value you should be thinking of is 1.999999, something very close to 2 but slightly smaller. And as you can see, this is close to the asymptote and it goes down and hits the function down here. So this essentially goes to negative infinity. Okay. Same with E, the limit as x approaches 2 from the positive side, so we're going slightly bigger than 2, so you should be thinking of 2.00001. So slightly to the right of 2, and again, this to go hit the function attains negative infinity. Same reasoning, limit as x approaches 2 of f of x, since the left-sided limit and the right-sided limit both tend to negative infinity, we can conclude that the limit as x approaches 2 is also equal to negative infinity. Our last example here, limit as x approaches 4 from the negative side, so slightly smaller than 4. Again, we're thinking of the value 3.99. If we look at a value close to 4 but slightly to the left, this goes to positive infinity. So here this is positive infinity. Limit as x approaches 4 from the positive side, so now slightly to the right of 4. If you go to the right of 4, so you're thinking of a value like 4.0001, that goes and hit the function down here at negative infinity. So here we can see that the left-sided limit gave us positive infinity, yet the right-sided limit, when we come from the right side, it's going to negative infinity. Since one goes on positive, the other one goes negative, what could we conclude about the limit as x approaches 4? So it's not positive or negative infinity. Here we have to write that it does not exist, the NA. The limit doesn't exist. The left-sided limit and the right-sided limit are not equal, so we say it does not exist. Okay, let's continue looking at examples. This is a visual illustration. Let's look at an actual function now. Okay, so in this example here, they're asking us to find the limit as x approaches 3 of this function here, 1 over x minus 3, all that squared. Okay, so here we don't have a graph, so we don't really know what the function looks like. We should have an idea, but if you don't, it's okay. So how do we start off by solving this? So the first thing we should do is always try to substitute this value into our function. So if we substitute or we replace x with 3 into here, what we get is 1 on top, and on the bottom, if you replace 3 in here, you get 3 minus 3, which is 0, 0 squared, which is also 0. So we get 1 divided by 0. And this is an issue, right? Because in math, we can't divide by 0. So dividing by 0 doesn't make sense. But what you have to understand is when we're dealing with limits, we're not talking about 0. We're talking about values that approach 0. Okay, so you have to really understand that difference, because it's not the same thing. So 1 divided by 0, if you plug that into your calculator, there's issues. But this isn't 0. This is a value that's super close to 0. So what we do here, well, first thing, notice that we don't have an indeterminate form. It's not 0 over 0, so that's good. But when you have a number divided by 0, you shouldn't be thinking of this as 0. You should be thinking of this as a number that's close to 0. So if you divide 1 by a very small number, what do you get? So you should try this on your calculator, put any number and divide it by something that's super small. What ends up happening, let's say you put 0.00001, you're going to get a very big number. And the smaller you make the denominator, the bigger the whole number gets. And this is a very important concept to understand when we're dealing with infinity. Okay, so 1 divided by a number that's super close to 0, or 1 divided by a very small number, makes the whole number larger. Okay, so take a moment, do this on your calculator, convince yourself. But this is a very important notion. Okay, so that's just the intuition you should have. But really what you should do is to determine whether this exists or not, we have to check the left-sided limit and the right-sided limit. So what you're going to do is start off and consider the limit as x approaches 3 from the left side. Okay. So 1 over x minus 3 squared. So if you're allowed to use a calculator, use a calculator. If you're not, what you should do is anticipate. Do you expect this value to become positive or negative? That's what we really care about. So if you're allowed to use a calculator, substitute your x with, instead of 3, a number that's slightly smaller than 3. So you could plug in like 2.9 or 2.9999 and substitute it into here and see what you get. But at the end of the day, if you don't have a calculator, what you have to figure out is this value on the denominator going to be positive or negative? So if we plug in here a number that's smaller than 3, so we're thinking of 2.9999, and we do 2.999 minus 3, well, 3 is larger, and 3 is the negative number, so you're going to have a negative number on the denominator, but it's all squared. So any number squared, think of like negative 2 squared. Make sure you put it in brackets if you're plugging into your calculator. You're going to end up getting a positive because 2 negatives make a positive. Negative 2 squared is the same as negative 2 times negative 2, right? 2 negatives make a positive. So this number on the denominator is going to come out to be positive. So we're going to get 1 over, let's say 0, but something that's slightly, not exactly 0, but very close to 0, very small. But what we care about is the fact that it's positive. So a positive number on the numerator divided by a positive number on the denominator gives us positive infinity. That's what we really care about. Okay. So when we check the left-sided limit, we got positive infinity. Let's check the right-sided limit. So limit as x approaches 3 from the positive side. So now what we're doing is we're plugging in the value 1 over x minus 3, all this squared. You're plugging a number in here that's slightly bigger than 3. So think of it as 3.01. So 3.01 minus 3 is 0.1. Oops. So again, 0.1 squared, let's say, it's still a very small number. Something very, very close to 1. But it's positive. And this is what we care about. The fact that it's positive, meaning that any number divided by a very, very small number gives us a very large number, namely infinity. But in this case, it's positive infinity. Okay. So since the left-sided limit and the right-sided limit both went to infinity, positive infinity, we could conclude that this value here on top goes to positive infinity as well. And that's the answer. Okay, let's take a look at another example. Okay, so this example here is similar to the previous one that we just saw. So pause the video, try it on your own, see if you can figure out the answer. So we're asked to find the limit as x approaches -4 of this function here, -2x divided by x plus 4. Okay, so let's go ahead and look at the solution together. So if we direct substitution the -4 into the x, we substitute the x's with -4, what we get on top is 8, and on the bottom what we get is 0. So we have a number divided by 0. So that looks like it's going to positive infinity, right? That's our intuition. Remember, this is not good enough. What you have to do in order to ensure that a limit exists is you have to check the left-sided limit and the right-sided limit. So here what you should be doing is taking the limit as x approaches -4 from the left side of -2x over x plus 4. So -4 to the left, so you're going slightly smaller than -4. So you're thinking of, let's say, -4.0001. If you substitute, let's just assume it's -4.001 over -4.001 plus 4. I'm just making it up. There's no reason why I'm stopping at 0.001. Really, we're thinking of a very small number. So if you want to put 18 zeros in between, that's fine as well. Or if you want to use -4.1 on your calculator, you could do that as well, just to have an idea of what's going on here, to evaluate this this number. Because we want to know, is it going to positive infinity or negative infinity? That's our intuition. That's what we're trying to figure out. And a useful tool, especially in the beginning, is to use, I would recommend, or strongly recommend, to use Desmos. Desmos is a good, like, solve your answer, and then after go look on Desmos to see what this function actually looks like. So now when we multiply this, we get, let's say, this becomes positive 8, slightly bigger than 8. And on the bottom, do we get a positive number or a negative number? Well, since -4.0001 is slightly bigger than positive 4, we're going to end up getting a negative small number. Let's put a bunch of zeros here and put a 1 just to say. So you're doing 8, or some positive value, divided by a negative of a very small number. So when you have a big number divided by a small number, this goes to negative infinity. Okay. So at the end of the day, you don't have to show all this. As long as you substitute -4 and you get negative, you figure out that the numerator is positive, the denominator is negative, and the denominator is going to a value that's very close to 0, a very small number. Then we could conclude that it's going to negative infinity. So this is the left-sided limit. Let's do the same thing with the right-sided limit. Limit as x approaches -4 from the positive side. So we're taking a number that's bigger than -4. So let's say -3.999, and we're going to substitute that in. Okay. So if you substitute -3.999, again, two negatives make a positive, so we know the numerator is going to be positive, and we know the denominator is going to be positive or negative. So we have -3.99, and this is +4. Well, 4 is bigger, so, and 4 is positive, so the denominator is going to be a positive value as well, which means that this goes to positive infinity. So what could we conclude about this limit? Well, the left-sided limit goes to negative infinity, whereas the positive side of the limit goes to positive infinity. So this over here goes to, well, this is negative, this is positive. We conclude that the limit does not exist because the left-sided limit and the right-sided limit do not match. Okay, so in this example here, we're asked to find the limit as x approaches 0 from the positive side of ln of x, and part B, find the limit as x approaches pi over 2 of tan of x. These are examples where they give us functions that we just have to know what they look like. Okay, so just as a reminder, this should have been seen in high school math. Your log functions, what they essentially look like is something like this. X, this is our y axis. So our log functions look like this. I'm going to draw the function in green. something like this. Goes to 1. And in red, let's do our vertical asymptote. So on the y-axis, the function here never crosses the vertical asymptote. Okay. So if we know this is the function f of x equals ln of x, now it's easy to figure out the answer. Because if we take the limit as x approaches 0 from the positive side, so the origin is here, so slightly to the right of the origin, so 0.001 is about here, and if we go down, we hit the function down here. So this gives us an answer of negative infinity. Okay. So this you would have to know from the graph. Okay. So the limit as of ln of x, or logarithm, log of x, same thing. The limit as x approaches 0 from the positive side is going to go to negative infinity. So this one you just have to know what the function looks like. Same for here. You have to know what your tan function, or you have to remember what your tan function looks like from high school. So if we sketch this, and if you don't, I strongly again recommend to use Desmos, because these ones come up often. So the function looks something along the lines of this. This is y, this is x. So again, the function is going to be in green. I'm just going to draw one variation. The tan function is periodic, it's going to repeat itself. I'm just going to focus on one period over here. So we have our vertical asymptote at negative pi over 2 and at pi over 2. Okay. So we have to figure out if the limit, what the limit as x approaches pi over 2 of tan of x is. Well, in order to do this, I have to extend, because this is not enough information. So if we look at the left-sided limit, so if we look at the limit as x approaches pi over 2 from the left side of tan, so we're looking over here, to the left of pi over 2 is about here, so it's going to hit up here to positive infinity. But if we look on the right side of pi over 2, let's draw this. The green function here, the tan function, repeats itself, so it's going to look something like this again. To the right of pi over 2 would be over here, which now goes to negative infinity. So the limit as x approaches pi over 2, from the positive side of tan x is negative infinity. The left-sided limit is positive infinity, the right-sided limit is negative infinity. What do we conclude about the limit as x approaches pi over 2? This does not exist, okay? Because the left-sided limit, the right-sided limit do not correspond. They don't match, okay? So these are two examples where you have to know what the function looks like in order to answer the question. There's other ways of getting around it, but this is one of the ways you could do it. It's easier to know what the function looks like. Okay, so let's take a look at a couple of harder examples. Okay, so let's look at this example. We're going to be dealing with vertical asymptotes now. And I think this is instructive to do as an example together. So keep in mind, when you're dealing with vertical asymptote, essentially what you have is you're taking the limit and you get a number divided by something that's very small, which gives us infinity. So a number divided by 0 is essentially when we're dealing with vertical asymptotes. Okay, so the question here is asking us to find the vertical asymptote of this function here, f of x equals x squared minus 1 over x squared minus x minus 2. What's different about this example here is they don't give us the limit. So we have to figure out where the vertical asymptotes can occur. Well, keeping this in mind that it's a number divided by 0, essentially what you're going to do is to find this is just one way of doing it, it's not the only way. I think it's the easiest. You want to know when the denominator is equal to 0. So that's our goal. Let's go ahead and find when the denominator is equal to 0. So this is step 1. Set the denominator equal to 0. Okay. So in this case, the denominator is x squared minus x minus 2. and it's equal to 0. So we have to solve this. One way of solving this is to use quadratic formula, because we're dealing with x squared, quadratics. My advice to you is always try factoring first. If factoring doesn't work, then refer to a quadratic as a backup. Okay, so this is a trinomial. The way we factor trinomials is something called product sum. So keep this in mind. I'm going to do this once on the side. So we have a x squared plus bx plus c. Okay, so a is the coefficient in front of your x squared, b is the coefficient in front of the x, and c is the coefficient, well, just the constant that's on its own. And the game that we're playing is we're looking for two numbers that when you multiply, it gives us a times c. And at the same time, you're looking for the same two numbers. Now when you add them, it gives us our b. So in this case here, our a times c, when we're looking at our formula here, the a is 1, because that's the coefficient in front of the x squared. The number in front of the x, don't forget the negative. So if you're thinking it's 1, that's wrong. Your b is negative 1. Don't forget to include the negative, okay? And your c is negative 2. Okay. So you're looking for two numbers that multiply that gives us a times c. A is 1, c is negative 2, so 1 times negative 2 is negative 2. So you're looking for two numbers that multiply that give us negative 2, and at the same time, two numbers that add, the same two numbers that add up to negative 1, which is our b. Okay. A trick to make here it's easy, but a trick to make this a bit less complicated is write down the factors of your a times c. So in this case, the factors of 2, ignore the sign for 2 seconds, just look at the number. We have a 2. Write down the factors of 2. The factors are 1 times 2. That's all that we have. So we know the numbers here are going to be 1 and 2. When you have larger numbers, let's say like 12 or 24, something with multiple factors, you have to look at which pair of numbers could you add or subtract to give you this value here. Okay, so we'll probably see this in future videos, but this is, in my opinion, the fastest way to solve the product sum method. So we know it's going to be 1 and 2. Now what we have to do is deal with the sign. Which one's going to be negative? Because we have to multiply these two numbers to give us negative 2. 1 times 2 is positive, so this doesn't work. Should we make the 1 negative or the 2 negative? Well, to answer that question, you have to look down here. Your b here is negative 1. So when you add these two numbers, you have to get a negative value, meaning that the larger number has to be negative. Okay, because 1 times negative 2 is now negative 2, and 1 plus negative 2 gives us negative 1. We found our roots. Okay, so this over here transforms into our roots. This is x plus 1, that was our first root, it's positive 1, and the second one is x minus 2, gives us 0. Okay. Now what we do is we use something called the zero product law. You're multiplying two numbers and that gives us 0. The only way to multiply two numbers and get a 0 is if one of those two numbers is 0. That's the only way you can multiply two numbers to give us a 0. Okay. That's why it's important whenever you're solving quadratics is to set everything on the same side, because you need the 0 on this side to use this zero product law argument. So either this bracket here has to be 0, so either x plus 1 gives us 0, or x minus 2 has to be 0. That's the only way for this statement here to be true. So here now we could solve for x, we bring the 1 over, it becomes negative 1. And here to solve for x, we bring the negative 2 over, it becomes positive 2. So the two values of x here that give us a denominator of 0 is negative 1 and 2. Okay. So if you stop here and you're like, the vertical asymptotes are negative 1 and 2, that's wrong. We have to be careful. So the second part to this is that we have to ensure that the numerator is not 0. Okay. That gives us a hole. We want a vertical asymptote. We don't want a hole. Okay, because we might have, if we sketch the graph, something that looks like this with a hole in it and then it continues. Okay, we don't want that. We're looking for a vertical asymptote. We're looking for something that looks like this. Okay. This is what we want. This is a vertical asymptote. This is a hole. So in order to solve this, what you do is you take these values here and you plug them into the numerator. And you have to ensure that the numerator is not equal to 0. Okay. So when we plug in, let's say for x equal to negative 1, if we plug this into the numerator, this is step 2. get x squared minus 1, that's up here, giving us negative 1 squared minus 1, 1 minus 1, which gives us 0. Okay, so this tells us that x minus 1 is not a vertical asymptote. It cannot be 0. Okay. Not a vertical asymptote. We have to ensure that the numerator is not equal to 0. So numerator cannot equal 0. Okay, that's your step 2. And now if we check for x equals 2, so x equals negative 1 doesn't work, x equals 2, x squared minus 1, plug in there 2, 2 squared minus 1, 4 minus 1, we get 3. Okay, so that's not equal to 0. So the only vertical asymptote that we have is at x equals 2. So we have determined that the vertical asymptote, which I abbreviate as VA, is at x equals 2, and that's the solution. So we have to reject this one here. Okay. So I hope that helps, and I'll see you in the next video. Keep practicing and keep working hard.